Okay, so here, say these are Panasonic TVs. These are Sony TVs. They're exactly the same as each other. So this is a Panasonic blah, 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 and a Sony blah, blah, blah. They've got the same specs. They're the same dimension. They're the same amount of, they're both 4K, or they both have all these other smart things. They're the same. They're identical in every way. The reviews are also the same. Like, everybody likes them a lot. The same amount of likingness, right? The difference is, if you look at these 6 reviews, this guy said, oh, it broke after 30 months. This broke after 35. Another guy said, oh, it broke after 40. Another guy said theirs broke after 35 months. So these 6 people happen to say how long it took before it broke. That's how long it went. So it lasted 30 months, and then it broke. These are a bunch of Sony TVs, and the guy said, oh, mine lasted 20 months, and then it broke. Oh, mine lasted 50 months, and then it broke. 40 months, and it broke. 70 months, and it broke. Oh, 10 months, and then it broke. Everybody understand? These are how long they lasted for each person before they broke. So first off, find the mean and range of each model. So find the mean and the range for this Panasonic model, and find the mean and the range for this Sony model. Everybody do that. Thank you. How do you find the mean? Find the mean of model A. So of those 6, add them up, divide by how many there are.
Not for me, because you just add them up and divide
And then find the range.
1, 2, 3, 4, 5, 6. And for range, you just find the highest and lowest of each of them. Right? No, that's not good.
So show your work. This divided by that. That would work.
Yeah, I guess you could put it in order, put it in.
You have to do the addition part, just the
It's just 30 divided by 0.
For the range? Yeah.
And then find your range for each one.
For me, everybody thought it made the difference. Wait, the range is the difference between the highest and lowest value. So it's just 40 minus 30. So it's the difference? I wasn't sure. I'm just kind of doing it by heart. Did you get 35 and 10? We need 35 and range 10. Wait,
But if you do 37, if you do 30,
she said me.
Oh, she said it out loud.
All right, so the mean. I'm going to add all these up, right? And divide by, so I get 210. So then my mean, my x bar for A is going to be 210 divided by 6, 35. What's my range going to be? The range is going to be my largest minus my smallest, 40 minus 30. 10. How about the other one? Add all these up. I get 210 there also. So my x bar of B, my sample mean of B, is 35, right? Because this is a sample. This is not every single TV of that style that Sony's ever made, right? They didn't make just 6 TVs. They made a whole bunch. These are just 6 of the reviews. So it's a sample. And my range is again going to be the highest and the lowest, so 70 minus 10, 60. Good? All right. So, both of them have an average lifespan of 35 months. Both of them will last, on average, Rob, thanks for volunteering. Go ahead and read.
Both models have an average lifespan of 35 months with the range for model A is 10 months and the range for model B is 60 months.
Right? So in other words, they both will last 35 months on average before they break. But Model A, the range of possible values is 10, between 30 and 40. Here, the range of possible months before it breaks is 60, between 10 months and 70 months it'll break. It might break at 10 months, it might break at 70 months. That's the range. Which one would you rather buy and why? Now talk to your neighbors, 30 seconds, and decide which one you'd rather buy and why. There's no right or wrong answer, just have a reason. All right, who would rather buy A? Who would rather buy B? Let's hear some reasons for B. Yeah?
I was just thinking there's probably a warranty, maybe.
Okay, there you go.
Fail.
Right, so what's up with buying, why did you guys say B? Yeah,
I mean, 60 is like a wider range compared to 10.
right.
It's not like guaranteed 10, so it might be 50, it might be 60. It doesn't always have to be 10.
So you're saying you want to gamble a little bit and maybe get lucky and get a 70, and maybe you get screwed and you get a 10, but you're willing to gamble a little bit, a little more risky. Now, who picked Model A? What are some of the reasons for that? Reason?
Generally speaking, you're probably going to get 35 months or so.
Yeah, it's a little bit more consistent, right? So generally speaking, this one is more consistent. And this one is it's a little bit of a gamble, but could be really good. Or bad. So it's just sort of that little bit. And like Michael was saying, if it breaks in 10 months, your warranty should cover it. So, the worst possibility is kind of is kind of taken care of. Definitely, you guys can see how this variance is really related to consistency, though, right? However, there are better ways to measure variation besides just range. So range is the maximum minus the minimum. It's very sensitive to extreme values. Not as valuable as other methods of variation. So we're going to look at variance, which is kind of the most common one. But in order to do that, first let's take a look at another way of thinking of average or mean. So, what's the mean of these 5 test scores? You add them all up. You divide by 5, how many there are, you get 80. Good? Average score of 80. Another way that 5 tests can average to 80, though, is if they're all 80. Everybody agree with that? Good. So what we do when we look at that is we take a peek and we see exactly how far each one is above or below our target number, our mean. So here, if you look at it, 75 is 5 below 80. 80 is right on 80. 83 is 3 above it. 77 is 3 below it. 85 is 5 above it. If we add up those differences, I better get 0, because otherwise 80 is not my average. Right? The average differences should be 0. So the problem is we can't just add up the differences, because we'll always get 0. So someone said, well, what if we square them all and make them positive first? So that's what they do with this variance. The first step we do is we take all those differences and we square them. So we square -5. I took out negatives here, but you get 25, you square 0, you get 0, you square 3, you get 9, you square -3, you get 9, square 5, you get 25. And then you average those. You add those up, divide by how many there are. There's 5 of them, I'm going to divide by 5. So then that's my variance, 13.6. Everybody understand how we got to that? We find out how far each value is from the mean. We take all those values, we square them, and then we average them. We add them up and divide by how many there are. That's population variance. So, so the differences, in other words, 75 is -5 away, right, from the mean. My mean is 80. 80 is 0 away. 83 is 3 away. 77 is -3 away. 85 is 5. Square all of them. So if I square 5, square 0, square 3, square 3, square 5. Or, this is -5 and -3. But square them all to make them positive. When you square a negative number, you make it positive. So now, there's always going to be positive numbers. So then, these are all the squares. I average them. I add them up, divide by how many there are. That's my variance. Do you guys want 15 minutes to talk, 15 seconds to talk to neighbors about it? Yeah? Take 30 seconds, go ahead.
So the reason for square is just to get a positive number?
Yeah, get a positive. Okay. Let me talk about something else. I'll do an example in a minute. So, you guys, we'll do another example in a minute. Give me a second here. So, here's the thing. We took the average of squared values, right? So, really, at some point, we should undo this square. How do you undo a square? Square root. So, at the end, what people do is often they square root this, and that's what we call standard deviation. So standard deviation is the square root of the variance. Except, you know what I'm saying? Because the variance is the average of all the squared values. You square root that, and that's the standard deviation. Let me give you an example. Oh wait, let me give you this first. So here's your formulas in your handout. So there's a fill in the blank here, guys, pay attention. For populations, right, populations in there. Variance and standard deviations and theoretical formulas are as follows. Sigma squared. This little circle with the tail on it, circle tail, you guys see it, circle tail, is called sigma. That's a Greek lowercase sigma, unlike the uppercase sigma we saw earlier, the sum symbol. Lowercase sigma. Sigma squared is our variance. Why? Because sigma is our standard deviation. So, how is the standard deviation related to the variance? The standard deviation is the square root of the variance, which means the variance is the square of the standard deviation. If you take the standard deviation and you square it, you get the variance. That's their relationship to each other. It's kind of like 3 is the square root of 9, then 9 is also the square of 3. Does that, you guys kind of follow me? So this guy, the variance is the square of whatever the standard deviation is. If you take this and you square it, take sigma, you square it, you get sigma squared. So if you take this, you square it, you get that. This is the square root of that. Right? You take sigma squared and you square root it, you get sigma. And that's exactly how you get them. This is the square root of that. This is the square of this. Adam?
So from the last problem, how we got like 13.6? So if we square root that, that's our
Standard deviation, exactly.
Okay.
Yeah. Are these statistics or parameters, guys? Parameters, because they're for a population.
Those are not the same.
No, this is a population variance. This is a population standard deviation. See what this has a little square root symbol over it? It's the square root of that. So if this is 9, if this one's 9, this one would be 3, the square root of it. They're not the same. The standard deviation is sort of, I'm going to say this one time, pay attention. The standard deviation is sort of the idea of, on average, how far are most values from the mean? That's kind of the general sort of gist of it. It's a measure of kind of typically, on average, roughly, how far are most variables, are most of the data values from the actual mean. And that's what the idea of standard deviation is. You know, kind of in general, more or less, how far are they away from the mean in general? And you guys are going to, people ask me that all the time. They kind of want a general sense, and that's the general sense of it. Let me give you a concrete example.
Listen,
Yes?
for the second definition, is that standard?
We haven't done that yet.
No.
Okay. Here's an example. My family. My family, there's 5 of us. That's the entire population. Right? Typically, you don't have a whole population, but if we're talking about just my family, there's only 5 of us in there. That's the whole population. Everybody on board? Okay. So my sister is 57 inches. My other sister, 58 inches. My mom was 62 inches. I'm 63 inches. My dad's 65 inches. Our average population mean, mu, is 61 inches. Right? If you add those up, divide by 5. All right, so then let's look at the variance. My sister minus the mean, that's -4. My other sister minus the mean, -3. My mom minus the mean, 1. Me minus the mean, 2. My dad minus the mean, 4. Then we're going to square all of them. Square them, square them, square them, so we get these numbers here. And then average them. Add them up, divide by 5, because there's 5 of us. Everybody on board? So then our variance would be 9.2 inches squared, because we squared the inches. And remember, the standard deviation is often more useful because it's in the same units. If I squared that, square rooted that, then all of a sudden I get inches again. Square root of 9.2 inches squared is 3.0 inches. So I would say, well, my family is on average 61 inches, give or take 3 inches, right? With a standard deviation of 3 inches. Give or take 3 inches. It's kind of a measure of roughly how far away from the mean we are in general, on average. Yeah?
So would it be right to say that variance is like the range of deviation?
Variance is, wow. You could say, it'd be accurate to say, variance is a measure of how much data varies from the mean. It's a measure. The problem is it's squared. It's a squared distance, so it's really hard to relate it to the actual, and squared, so the units are squared also. But it is a measure of how far, obviously the bigger the variance, the more crazy the numbers are away from the mean. The less consistent they are. The smaller the variance, the more consistent they are. The more, the closer they are to the mean typically. So the TVs, right, model A would have had a very small variance, and Model B would have a fairly large variance. Okay. In fact, I think we're going to compute those. So yeah, so the idea of variance is exactly like this might answer your question, maybe what you were asking is, but determines how consistent a variable is, and how spread apart the data is. So here, this data has no spread. You guys see that? Everyone look up. This has no spread at all. They're all the same. It's just 1 point. They're all the same spot. Whereas this one has a lot of spread. Right? It's not very consistent. It's kind of all over the place. All right, so now we're going to talk about sample variation. How about, Allie, go ahead.
Almost all of what we will be doing in this class involves samples of data. We are trying to estimate the variance of or standard deviation of a population from a sample only. It is often too small due to the fact that we are only using a sample versus the population. To adjust, we divide by n minus 1 instead of n. This is what we call the sample variance as equal standard deviation.
Right. So often a sample will be not quite, usually we're working with samples, right? It's harder to get the whole population. It's just difficult to get them all. So when we do that, often our mean will be off a little bit because it's a sample mean, not the actual mean itself. So very often our data is going to be off a little bit. So which means that our standard deviation and our variance is going to be off a little bit. It might be too small. So we adjust for this and give ourselves a little more room for error by making it a little bit larger. How to make it a little bit larger? We divide by n minus 1 instead of dividing by n. So say I got $20, and I'm going to divide amongst these, let me find 5 people. These 5 people, right? About $20, I divide amongst these 5 people, they each get how much money? $4. Everybody on board? But if I take that $20 and then divide, instead of dividing by 5 of them, I only divide by 4 of them. Divide by n minus 1. Divide by 4, how much do they each get? $5. They get a little bit more. So when you divide by a smaller number, it makes it, everybody gets a little bit more. Your answer is a little bit larger because you're splitting up amongst fewer people. So dividing by n minus 1 makes the number a little bit larger because our sample, when our sample is small, our data is just more likely to be off a little bit. It might be clumped or clustered in some way that we're unaware of. The nice thing about this is someone brought up last class, they said, well, what about when your sample is really big? The beauty of that is when your sample is really big, like 1,000, then your sample is pretty good then, right? You're more likely to be close to the actual mean. Dividing by 1,000 versus dividing by 1,001 is hardly any difference at all. You'll hardly get any difference at all. So that's why when n gets really big, this dividing by n minus 1 makes almost no difference at all. But when your sample size is small, like 5 or 6, when you're likely to be off by a fair amount, then it makes a pretty large difference. Okay. So bottom line is, for a sample, so this is the next line of your notes, for samples, we use a sample variance. S squared for variance and S for standard deviation. Sample standard deviation. It's exactly the same as the previous one for the population. Only difference is that instead of mu, we have x bar, right? So instead of our population mean, we have our sample mean. And instead of n, we have n minus 1. Because it's a sample, so we divide by n minus 1 to give ourselves a little more room for error. So sigma is the Greek letter for S. S is the, what do you call it, the English letter? For S is just S. So the sample ones would just be regular ordinary letters. S squared. Whereas the population ones would be the Greek ones, sigma and sigma squared. All right, everybody on board with this so far? Okay, we don't have a lot of time, we gotta get going. So let's take a look at an example. Find the variance and standard deviation for the sample of how long TVs lasted in the earlier example. I will do the first one with you. Here we go. What was our sample mean again for this? You guys remember? 35. X bar is 35. So first I'm going to do every value minus the mean. So we're going to try to fit in 2 lines here, so write small. This is the first one. How far is 30 from the mean? From 35. It's 5 below it. Everybody agree? How far is 35 from 35? 0. 40 is 5 above it. 35 is 0. 30 is 5 below it. 40 is right on it, 5. Everybody good with that part? You should be all writing this in, right above yours. And then we're going to find x minus x bar squared. We're going to square all those. So negative 5 squared is 25. 0 squared is 0. 5 squared is 25. 0 squared is 0. Negative 5 squared is 25. 5 squared is 25. And then what's the next step we do? We're going to add them up and divide by, we're going to average them. Add them up and divide by how many there are. Oh, divide by n minus 1. Almost by how many there are. We're going to do a slight variation of that one. So then we're going to add them up and divide by n minus 1. So let's add them up. And I'm going to divide by how many of them are there? 6. So I'm going to divide by 6 minus 1. That's going to give me 25 plus 0 plus 25 plus 0 plus 25 plus 25 is 100. 6 minus 1 is 5. So it's going to give me a sample variance s squared of 20, right? 100 divided by 5. And that's going to give me a sample standard deviation s of square root of 20. Good? You guys do the one below that on your own. Does everybody see where we got these from? Yeah. Normally divide by how many there are, normally divide by n, but because it's a sample, we divide by n minus 1 by 6. You know, that whole talk I just gave about it being a sample, you gotta make it a little bit larger. $20 divided by 5 people versus $20 divided by 4 people. If I square all those amounts, I'll get 225. Hey, you guys, come back to me. I'm going to go over this. So you got maybe you'll figure it out from there. So if you're not sure what to do, I'm going to do it now. Pay attention. I found out how far each one is from the mean, 35. This is 15 away. That's 15 away. That's 5 away. That's 35 away. That's 25 away, and that's 15 away. Now you need to square all those differences, right? That's what because this part is the difference. Square all of them. 15 squared is 225. 15 squared is 5 squared is 25. 35 squared is 1225.
Correct.
25 squared is 625. 15 squared is 225. And then we need to average those. Kind of average them. Add them up and divide by n minus 1. So I'm going to average them, sort of, by adding them up, dividing by n minus 1. Add. Divide by, what am I dividing by? How many are there? 6, so 6 minus 1. So then we're going to get 25, is it 2550?
Yes.
Divided by 5. So it means that my s squared, my variance, right, variance, is 510. And my standard deviation, s, is square root of 510. So like, I have no idea what that is. What is it?
22.58.
22.58, 22.6. So 22.6 versus 4.5, that's a lot larger, right? Much bigger variance. And much bigger standard deviation. So in general, they vary. You know, these TVs will last 35 months, give or take like 22 months. It's pretty big. This lab problem, everybody write very neatly for this one, for the blue chip, the chocolate chips. We're going to skip that one because we just did the other one instead. That's fine. So right, skip there, just on this one. All right. Here's some notation. We've got three things to cover before you guys go. This is the first one. The notation. S, that's your sample standard deviation. S squared is your sample variance. Why? Because if you have your sample standard deviation and you want your variance, you just square it. If you have your sample variance and you want your standard deviation, you square root it. Right? That's how you get from one to the other one. Sigma is your population standard deviation. Sigma squared is the population variance. So if you take this and you square it, you'll get that. If you have this and you want this one, if you take this and you square root it, you'll get this. That's how they're related to each other. Okay?
Will you read that for me, please?
Yes, I can leave it for just a moment.
Here, I'll just take a picture of it.
Yes. They're in your notes, right? So there's this whole stuff.
It's just backwards though. That's why I think.
Yeah, there's a whole bunch on the bottom. So you should just figure out where they go on the sheet at the very bottom of your page. They go in different places. Okay. Now, figure out where everything else goes. I'll give you guys a minute to figure out where the rest of these, fill in the blanks for the rest of these. And then we'll go over it. Working with your neighbors, we'll go over those.
Yeah.
All right, so let's go through these. The sum of a set of values. What's the symbol for summing them? Anyone?
The backwards.
Backwards E. That's the sum.
Or backwards.
The variable usually used to represent the individual data values, each individual one. X. The number of data values in a sample. Small n, little n, that's our sample size, good. Number of data values in a population. Capital N, great. Pronounced X bar, and denotes the sample mean, your sample mean. X bar, good. Mu, denotes the population mean. That's mu, our population mean. Sigma squared, that's our population variance. Sigma, our population standard deviation. And then we have variance, sample variance. Variance is always the squared one, S squared, and standard deviation of a sample. Sample standard deviation, S.
Yeah.
Good?
It's on that.
All right.
It's a weird.
Now, here's the thing.
No, she didn't. She just.
There will be a few problems in your homework, I think, where you might need to use a computational model instead. It's easier to compute instead of going through, especially when you're dealing with, like, ours is fine when you're dealing with like 5 or 6 items and your sample mean is a whole number. When we start getting to decimals and sample size is larger than 5, then it gets more complicated. So it's a lot easier using this computational model. I kind of don't like it in a sense because it's not intuitive in any way. You have to memorize it, kind of in a way, not memorize it, but you have to write it down. So I would recommend writing it down on the previous page, right here next to, for samples, variance and standard deviation, and theoretical formulas. I'd write it down in that corner right there on the previous page. It's right here. That's the sample variance. Sample standard deviation would obviously be just the square root of that. So I'd write that down, and I'll explain to you what it is. So n, your sample size, times the sum of your x squareds. Some of the x squareds mean, some of the x squareds means you take every x and you square it first, and then you sum them. This means you square them all first, and then you sum them. Minus the sum of the x's, that means you take all your x's and you add them up first, you sum them first, and then you square it. Right? So you do this first, and then you square it. Divided by n times n minus 1. So that you might find, I think you'll need that for a few of your homework problems. That's it. Have a good weekend. I will send out, once I grade your exams, I'll post them on Connect Math, your exam grades, and then I'll email you through Connect Math to let you know that they are available. So check your Zone mail for that notice. It'll be sometime this weekend. Probably Sunday, maybe Saturday.